Okay, so let's dig into some of these properties of definite integrals now. And I think that we can make sense of these properties if we continually think about the fact that this notation again refers to area. So this is saying if you have a constant function and you're looking for the net area bounded by that constant function in the x-axis. I mean, we can even think about this. Let me just sketch this out real quick, and then I'm going to erase it because I need the space. But I've got a constant function, and I'm going, let's say that this is y equals c, and I'm going from x equals a to x equals b. So if I'm looking for the net area bounded by the constant function c in the x-axis from x equals a to x equals b, well, that's just one big rectangle, isn't it? The height of that rectangle is c, and the width of that rectangle is b minus a. And so we can just reason that this integral of a constant is just going to be the constant times b minus a. So I'm just going to write that in here. So we'll say c times b minus a. This one right here, this is saying when you do the net area of one function plus or minus another function, well, we could kind of sketch things out and do it the same way that we visualized in number one. We will see that this is equal to the net area of that first function going from a to b, and then we'll say that there should always be that dx in there, plus or minus the net area of that second function from a to b. And so in this sense, this actually shares some similarities with properties of indefinite integrals that we looked at back in 5.1. But again, at this point, we're not connecting this at all to indefinite integrals. That's what's coming in 5.4. Right now, we're just thinking about area and properties of area to come up with an equation like this. Likewise, we can come up with another property where if you're doing the definite integral of a constant times a function of x, that constant would be in there, right, with all of the rectangles, and so you might as well just pull that constant out in front. So it's this idea of a constant multiple rule in a sense with definite integration, and we saw that with indefinite integrals as well, or just antiderivatives. Okay, this one right here, this is saying the integral of a function from a to b, so you're going for the net area of a function from a to b, but then we're adding in some additional net area from b to c. Well, in the end, that gives us the total net area of our function from a to c. This is kind of an interesting property, and it's a little bit of a difficult one to justify, but if you are doing the integral of a function, and remember that's in this case when we're talking definite integral of a function from a to b, that means you're starting at a, you're ending at b. If you switch the a and the b around, then what ends up happening is you end up negating everything in that original limit definition formula. And so the effect in terms of a definite integral or properties of area is that the integral of a function from a to b is equal to the opposite. So this question mark should be a negative. It's equal to the opposite of the integral from b to a. And then this one is saying the net area bounded by f of x in the x-axis from a to a. Well, if you're starting at a but you're not going anywhere, then that's not giving yourself any area whatsoever, and so that's actually equal to 0. Okay, so let's try to apply these properties in these examples here. So number one, it says let's do the net area bounded by the function in the x-axis from 2 to 12, and we know the following. Well, can you see that the net area bounded by the function in the x-axis from 2 to 5 is equal to 8, and then from 5 to 12 is equal to negative 3. So doesn't that mean that there's more area below the x-axis from 5 to 12? But if we want the net area from 2 to 12, then can't we apply this property right here, number 4, and say, okay, well, we can simply say, let's do the net area from 2 to 5, and then add in the net area from 5 to 12. And so the net area from 2 to 5 was 8, and we can add that to the net area from 5 to 12. And so 8 plus a negative 3 here, if you do 8 plus a negative 3, you get your final net area of 5. And if we flip those limits of integration, that's this property, property number 5. This would just be equal to negative 5. If we say, let's look at the net area going from 2 to 2, that's this property. There is no area. If you're not extending anywhere beyond x equals 2, then you're not giving yourself any space. And then here's one that kind of puts it all together. And this is actually a pretty tricky question. It applies property number 2, but it also applies property number 3 a couple of different times. And then it also applies property number 1. And it's property number 1, believe it or not, that people miss a lot. So if I was doing this question, I would do it the following way. I would say this is the integral from 2 to 12, and I'm going to pull that 7 out of 7 times f of x. Then I've got plus, I can pull the 3 out from the next one, plus 3 times the integral from 2 to 12 of g of x. And then a lot of students make the mistake of just saying, oh, it's just going to be plus 8. But it's not. It's plus the integral of 8, or the definite integral of 8, going from 2 to 12. This one, let's see, are we given this one? We are given the net area from 2 to 12. We actually found that before. That was equal to, in part 1, that was 5. So we have this is going to be 7 times 5. Then we're going to have plus 3 times the net area of g of x from 2 to 12. And that's given. The net area from g of x between g of x and the x-axis from 2 to 12 is equal to 15. And then we have to add in not 8, but it's going to be, this is a constant times, you can see this property right here, b minus a. So it's going to be 8 times 12 minus 2. And so this leads me to 35 plus 45, so that's 80, plus 8 times 10, so that's another 80. So that gives me a grand total of 160 here. So this is an excellent example in question 4 that kind of puts all of these properties together. Okay, a few other miscellaneous things here, and then we will jump into some practice questions. I said a function must be continuous over an interval in order to be differentiable over that same interval. But that was with derivatives. And this is not a requirement with integration. A function with a finite number of jump discontinuities can still be integrated. So a jump discontinuity, kind of like what you see in this picture down here, you can see that the function kind of ends here and then it jumps down. Jump discontinuity is fine. You could still find the net area bounded by a function in the x-axis when you have these jump discontinuities. But infinite discontinuities cannot be integrated over that interval. That's actually something that you'll end up dealing with in Calc 2 a little bit. This is basically saying if you have a vertical asymptote or something, like if I just kind of sketch this in, like if this is y equals 1 over x in the first quadrant, since you have a vertical asymptote there, you can't technically integrate this function from 0 to some other number, because when you go from 0 to some other positive number, there is that vertical asymptote right there at x equals 0. Okay, so in the picture over here, I said let's calculate the value of the net area bounded by the function in the x-axis from 0 to 6, given what we have in black. So basically we need to find the area in black. And one of the big things that you're going to notice in this section is we are actually not relying on any special theorems or anything like that. We're just going to rely on geometry. And here what I'm going to do is I'm going to break this up, and I'm going to break this up into a couple of things. And so I've got a triangle here, and then I'm going to break it up into another triangle there, and then a rectangle, and then a semicircle. But let's see if we could do this. So the height of this triangle is 3, the base is 2. So if we do 1/2 base, half of the base times the height, so that'd be half of 2 is 1, 1 times 3 is 3. So that first triangle has an area of 3. This one right here looks like we have a base of, that was going from 2 and that's going over to 4, so base of 2, but that height is 1. So half of base times height, half of 2 times 1 ends up giving us 1. And then this one, base times height, that's 2 times 2, so that ends up having an area of we don't have, I'm sorry, we don't have to do half base times height. Here it's a rectangle, so we just say base times height. So 2 times 2. So that rectangle has an area of 4. So this triangle has an area of 3. This has an area of 4. This has an area of 1. But we've got another semicircle. And you can look at the semicircle and notice that the radius of that semicircle is just 1. So what is the area of a semicircle? Well, the area of a semicircle is half the area of a circle. And so the area of a circle is pi r squared, so the area of the semicircle is pi r squared divided by 2. But our radius in this case is equal to 1. And so we end up with pi times 1 squared divided by 2, or simply pi divided by 2. But when I'm doing a definite integral from 0 to 6, like I am in this case, and 6 is where this point is on the semicircle, then I'm doing the net area bounded by the function in the x-axis from 0 to 6, where anything above the x-axis is positive and anything below is negative. So I'm going to subtract off the area of my semicircle. I'm going to subtract off pi over 2, and this is going to give me 8 minus pi over 2. So if I just come over here and say 8 minus pi divided by 2, I get about 6.4 or so. So we'll just write that, 6.429. Okay. And so when you start thinking about these definite integrals as truly being these net areas, and that's what I'm really trying to emphasize in an example like this, then you can make some conjectures about integrating certain types of functions. For instance, if we take a look at a classic odd function like y equals x cubed, so here's y equals x cubed. So if I asked you for the net area of y equals x cubed, going from, I don't know, let's say that this is like -1 up to +1. So we've got this area in here, and we've got this area in here. What do you think that this would be? Well, remember, any areas below the x-axis end up being negative, and then any areas above end up producing positive results. But you can see that we have symmetry here, don't we? And so the idea is when you're integrating with an odd function, these are just little tidbits. What you see in 2 and 3 are not major things that you're going to take with you moving forward, but they're minor things that you might be able to apply in certain contexts. So if we did the integral of x cubed from -a to a, this would be equal to 0. And it doesn't have to be just x cubed. It can be any odd function. And so that's the idea here. That right there can be any odd function, because odd functions have symmetry with respect to the origin. And so whenever you integrate a function that has symmetry with respect to the origin, then you'll end up with this idea right here. And then with an even function, you could look at like y equals x squared. If you apply the same thinking, y equals x squared looks like this. So if you integrated a function from like -1 to 1 here, we have symmetry again, but everything's going to be positive. And so instead of saying, I'm just going to do the integral of my odd function going from -a to a, we can state that this is actually equal to 2 times the integral of that odd function from 0 to whatever that a value is. So you can kind of utilize the symmetry idea to help you out. Okay, so in the next video, I'm going to put this all together in some practice problems, and then I want you to apply this in the homework. Again, the two big things are interpret definite integrals as net areas, where anything above the x-axis is positive and anything below ends up being negative, and you put it all together in the end to get your overall net area. And then also, as you're doing the homework, do your best to apply these properties of integrals that you see here. Okay, thanks.